Hi everyone, thank you very much for coming, and thanks a lot to the organizers for inviting, and to ML in PL organizers for making like all of that happen. So so today I wanted to tell you about one of our recent work, which is Google Research Football. Before I start, I just want to mention something about the team. So I'm from the Google Brain team in Zurich, and we are a team of around 20 researchers working on fundamental issues in machine learning. So we are not really tied to some specific products. We can deal with problems that may be beneficial to researchers or to Google in 2 years in the future. So the general topic of the team is representations for reinforcement learning. And this is a very broad topic. As you may know, there is already the whole conference on representation learning. But just wanted to mention bigger recent efforts from our team, which are generative adversarial networks. We had some recent work on disentangled representations. Maybe you have seen there was an ICML best paper from our group on disentangled representations. We also have some recent work on transferable representations. And today I wanted to focus on our paper about Google Research Football. So the talk will be about this paper that just got yesterday accepted to the Deep RL workshop, and it's in submission for AAA. And before I start, I wanted to mention that obviously it's a big collaborative effort, and the work that I'm going to describe is the result of work of all of those people. All right, maybe discuss some motivation. So I guess all of you are familiar with the setup of reinforcement learning, that we have some environment, we have agent that acts in this environment and gets some observations and rewards. RL, it's used a lot in real world, so probably you have heard one of the results was that the Google data centers are actually cooled by mechanisms that was trained using RL. Also, self-driving cars are utilizing RL, and probably robotics currently is one of the very big users. But there's a problem with RL in real world. So it may be very difficult and expensive to set up, and also it's not very easily scalable. So you cannot just get thousands of robots easily, while computers you can. So what people are doing, they are replacing robots with video game simulations that are easy to use, they're relatively inexpensive, that can scale well. They also provide a safe environment for experimentation. And there was lots of recent progress in reinforcement learning due to the use of games such as Atari or Go. And so there is a wide range of environments that people are using, and there are different trade-offs between them. So some of them may be actually very easy to solve for the state-of-the-art algorithm, and you just run it and you get for example Atari, the 50 games from Atari, using current state-of-the-art you can very easily get to the superhuman level. At the same time, there are expensive environments that can really model very complex dependencies, but they may be very hard to run out if you are not in one of those big labs such as Google or OpenAI or Facebook, because they may require hundreds of thousands of CPUs, and in general be super costly. There is also a wide range of other environments, but some of them may be really specific to a given problem, to robotics or only to multi-agent setup, or they may assume that the model of the world is actually known. So what we did recently to advance the research in RL, we proposed the new environment in which the goal of the agent is to master the game of football. And as you can see, the game is modeled similarly to popular video games such as FIFA or Pro Evolution Soccer. So here, the goal of the agent is to control the player, learn how to pass, how to tackle the opponents, and do other things in order to score a goal. And the Google research football consists of 3 components. So the first component is the football engine, which is based on an open source gameplay football game. There is football benchmark, which is essentially a set of problems, like a full 11 versus 11 games, together of various difficulty, together with baseline results on some of the state-of-the-art algorithm. And we also provide Football Academy, which is like a set of smaller tasks of progressive complexity that you can use, like maybe like as a unit tests for your RL approaches, and just see very quickly if things are working or not. Right. So I wanted to start with describing the football engine. So the football engine is, as I mentioned, is based on the simulator gameplay football. So we heavily modified the source code and we made it faster, more suitable for the RL research. We fixed like a number of bugs. Like one of the things that we did, for example, we detached the simulation from the rendering. So you don't need the GPU and you can very easily scale it. The whole environment is easily accessible through the Python bindings. You have standard OpenAI interface. As I mentioned, the game was speed up significantly. Our engine implements a full football game with like all of like the usual rules, such as like kickoffs, offsides, yellow cards, corners, and free kicks. The length of the game we measure in terms of frames. So our game, like the full game, consists of 3,000 frames because we ask the agent to perform action every 10 times per second. And finally, everything here is very easy to customize because, as I mentioned, the code is open source. So whatever you would like to change, get rid of this part or maybe set up players differently, you can very easily do so. All right. So the default opponent in our environment is like a rule-based bot, and the difficulty level of this bot can be very easily adjusted because we have a parameter between 0 and 1 that you can control. And by default, the rules how this bot behaves are so we have 2 things, right? So one thing is the bot that is our opponent that we can adjust, and the other is the built-in AI that's controlling the player, the non-actor players, and this is following the standard rule. So it tries to move along the active player. It tries to move in the direction of the other goal, and it basically tries to position itself correctly. It's basically like if you ever played FIFA. It's almost the same behavior. All right. Another very interesting feature of this environment is that we, out of the box, support the multi-agent. So, as you may know, in environments like Atari, even if you have other players, they are usually part of environment. You cannot really control it. In our environment, you have 2 options. You can either say that, okay, you have the standard setup that you just control the active player that gets the ball, or you can say that actually you would like to provide the actions for all of the players, and then they can execute something. Right? So our environment provides also a very easy way to train in a multiplayer setup. So, for example, you can train a model and then later play against it, or you can actually play, let 2 models play each other, which allows for a very easy self-play scenario. Right. Regarding action space. So basically what we support discrete action space. It's quite easy to change it to the continuous, but currently we only expose the discrete action space with 20 different actions. And those are 8 movements in different directions. There are different ways of passing the ball, high pass or long pass or shooting. We also have some actions for dribbling, sprinting, and also some actions related to goalkeeper. And here I just wanted to mention that like you may see one action slash the other action is because depending on which mode are you in. Like if you have a ball, this button may be like a high pass, but if you don't have a ball, this button may mean like a sliding tackle on the opponent. Okay, and one thing is that for some of the actions, like movement and sprinting, we just assume they are sticky. So like when you press sprint, we assume the sprint is just pressed, and then you have to do like another action to stop sprint, to undo it, because otherwise it will be maybe a bit more complex to control it. Right, rewards. So basically we provide 2 rewards in our environment. I mean, it's very easy to add another one. We have some wrappers for this, but yeah, so here's like the scoring reward, which is like, I would say, the most natural one that you can think of football. So basically, you get a +1 point if you score a goal, and you get -1 if you lose a goal. However, this is a very interesting problem, right? Because this is a sparse reward, and the whole branch of sparse reward training is it's very interesting, but it may be sometimes too hard, right? Because in order to get this reward, and like when your agent plays randomly, it may require you to get like close to the goal, like go around like the defenders, and then overcome the goalkeeper. So in addition to that, we observe that one very simple trick works quite well. So we also provide a helper reward that's giving you some small reward for getting closer to the goal. So how it works, we define this space on the opponent's half into like 10 spheres, kind of, and like crossing each of those gets you like 0.1 reward. But you can collect it only once. So you cannot like go back and forth and collect enough rewards so that scoring doesn't matter. Yeah, I mean that would happen, right? If you could collect it into 2 times. All right. Regarding representations, we support several types of representation in our environment. So the most basic one, returned by the environment, is the floats. So that could be positions of the players on your teams, positions of the players on the other teams, velocity vectors, how tired are the players, because if you sprint, this actually affects the tiredness. So that's one kind of representations. We provide the raw pixels, obviously. So like if you want to train from raw pixels, that's possible, but obviously it's much more costly. We also provide the training from minimap and from stacked minimap. So here minimap is just like a 0-1 position of the players, and here at the current frame, and here the stacked minimap is like the same, but like we allow to look a bit into the past. So like, for example, if you want to determine from that ball goes from one point to the other, this might be useful. And yeah, like for all of those, really no GPU is required, and you can train very quickly on the CPU alone. And speaking of very quickly, so I already mentioned that we optimize it like really heavily compared to the original gameplay football game. And currently, on a single hexacore machine, we can do 140 million steps per day. So, like on a single machine, you should be able to train most of the benchmark in like, even on hard difficulty, in like around 3 days. And yeah, so I think it's actually a very, very nice advantage that you don't need like a huge TPU pod or like thousands of CPUs to really try some simple ideas. All right, football benchmarks. So as I mentioned, the goal of football benchmarks is to provide like some standardized setup for a full football game that people can compare to. So like you're working on a new training algorithm, you could use the benchmarks to compare. So the task here is we play normal game, 11 versus 11, with a full length, which is 3,000 steps, versus the rule-based opponent. And we provide the rule-based opponent on 3 difficulty levels, easy, medium, and hard. So you can see how the algorithm behaves. And regarding algorithms, we used three state-of-the-art algorithms to provide the numbers. So one is the PPO from the OpenAI baselines. We used Impala, which is like a very scalable algorithm that disentangles like actor and learning part. And we used also like a scaled DQM version. And okay, so what is important for all of those experiments? We really try to be as fair as possible. So we use the same network architecture. We use the same representation. For all of them, we run 5 seeds and average the results. What else? Yeah, I think the biggest difference is like for PPO, because we use the OpenAI implementation, we only had a version that runs on one machine, so we were able to do like less steps, but we report the results at the number of steps. Okay, so here you can see the results. So on the left, you see when the reward is only scoring, okay? On the right, when the reward is like the checkpoint reward, so this is our like small reward shaping to give you advantage for going towards the opponent's goal. So first of all, we can see that for the easy difficulty, which is blue, I'm not sure how visible it is, but here is the PPO at 50 million steps, and here is Impala at 500 million steps, right? And here is actually PPO at 20 million. So you can see that even for the simple scoring reward, they are all actually able to solve it in like reasonable number of steps. And we can also see that actually the difficulty of the opponents affects the training time quite a lot. So for the medium difficulty, we already see that this is the task already gets harder, and for scoring, actually only the distributed Impala was able to get a positive score if we are not using any reward shaping. And yeah, reward shaping seems to be actually useful, because here you can see the result is significantly better. And for the hard scenario, even if we put over like 500 million steps in it, we need first of all distributed training, and we also need reward shaping. So yeah, so it seems that the current state-of-the-art methods can solve it with some help of shaping and enough of training steps, but there is like lots of room for improvement here to try to decrease the sample complexity, for example. All right, and the Football Academy. Right. So as I mentioned, like training this full game may be challenging to some of the methods, especially if you want to use the simple rewards. So we decided to create a set of smaller tasks that are quite diverse, and they can allow you to test your ideas quickly. So, you know, for some of those tasks that are the simple ones, you can think like really as a unit test for your approach, and you can get results in several minutes, maybe even. So the Football Academy provides 11 tasks of actually I think yes. So I have a slide here. So here you have an example of the Football Academy task. So here, for example, there are like 5 opponents behind you, and you need to learn to sprint to the right in order to avoid them, because otherwise, if you don't learn to sprint, they will catch you and they will take the ball over from you. In this scenario, I think this is like a counter-attack. It's like, you know, what happens when you're like 3 versus or like 4 versus 1 on the opponent's goal. Here's the corner, and here's a scenario that requires you to learn how to pass the ball. Alright. So here are the results for all of the academic tasks, and first of all, you can see that they really vary in terms of difficulty. So like here's when you are close to the empty goal, so this is this scenario, like Impala is able to solve it on like every difficulty level, no problem, but it starts getting trickier when you have, I don't know, some hard counter attack or like some kind of 11 of 11. PPO does a little better because of like better sample complexity, but still some of the problems are like corner or the surround to score. They are also quite challenging for PPO. Alright, so I wanted to show you like some of the interesting examples that we run into when developing this environment. So this will be, okay, so this is actually a movie from one of the, okay, so what's happening here is that the agent that is playing realized that it's weaker than the other opponent. So what you end up doing, I'm not sure if you can see, it's like some auto rendering, but basically here you see the goalkeeper that's like running around and doesn't want to resume the game because it knows that, okay, if it resumes the game, it will lose even more, right? So it's better to just like keep running here, wait for the game to finish, and then yeah, you just lose 1-0 and not like 10-0. I mean, this is some older version. I mean, we obviously change it to not allow running, but you know, this is kind of like unexpected thing that they actually allow it in the original game, and yeah, you need to think about that. Another example that I liked a lot. So like, okay, here's the scenario. So you know, there's on the opponent team there's only one player. There's only goalkeeper, and you have to score a goal. So what do you do? So like normally, probably you would assume that okay, the players go to the right. Maybe they try to pass the goalkeeper, or maybe they just try to pass to someone else, and then like then to score. But actually, then I figured out another interesting way to do this. So actually, okay, if there's only goalkeeper, let's move the ball to the out. Then someone has to throw it in again. there is only goalkeeper. So now the goal is empty, right? Because the goalkeeper is here. It has to return. So it's much easier to score this way, right? So those are some interesting things that you run into. There is actually one other thing that I don't have slide to, but our original action set included, like, if you ever played FIFA, you know there is another button which means like a switch the active player. So like when you are defining, you can switch the player to like, you know, be closer to the ball to something. And we had this action in our action set, and what started happening was that the bot figured out that, okay, the most optimal action is to always switch, because then the built-in AI will take care of the other built-in AI, and it doesn't have to learn anything. So, yeah, so in the end we decided to remove this action because it was converging to the local minimum. All right. I also wanted to briefly mention some of the interesting research direction that we thought about would be maybe cool on this environment. So, multiplayer is one of the things. So, as I mentioned, the environment supports multiplayer out of the box, and we run a bunch of experiments with such a training. But I would say that the problem is that it's not really transitive. So you may train, let's say you train agent A versus some built-in AI, and it does well, right? Then you train some other agent B versus the agent A that was doing well. Okay, but now you let the agent B, who is like beating this one like crazy, you let this agent play against the built-in AI. Then actually it loses, right? So the problem is like not really transitive, and yeah, the question here is like how to make it somehow robust, how to make those agents robust against like a different variety of opponents. Yeah, one idea is to maybe play against like a previous version of cells, but there may be other ideas that would be worth exploring. So another interesting thing is learning from raw observation, like raw pixels, for example. So as far as I know, except of Atari, there is no real success for training like RL from pixels, like StarCraft, Dota, and I think most of the other stuff. They are training from raw observations. So to have a system that really looks at like what's happening in the field and then learns to play in an efficient way out of this would be actually very cool. And we had some initial experiments. So we moved pixels to the grayscale, we downscale it a bit, and we ran the training for 500 million steps. And it wasn't as good as Minima, but actually it managed to get better results than raw flows, which was very surprising to us. So,
but the raw pixels in Minimap poses the problem partially observable, right? Because the flows include all the information, or only about the active player too?
No, the flows contain all the information.
Okay. But in the raw pixels, do you have information about how exhausted is the agent you play?
No, you are losing some of the information actually.
So yes, this is interesting.
Yeah. I mean, it also requires so basically we use the same, that's more or less. I mean, for those we use convolutions, and here we just use the NLP. Maybe it requires more tuning, but I mean, it was also quite surprising to us. But maybe it's also somehow those convolutions are easier because then, when players are close, the convolution can get this concept that okay, there are players here and maybe there are players there. And here you would have to learn some kind of relation that, those two players are close.
Just learn better representation.
Yeah. Yes, I mean, so this is so we did a bunch of those smaller experiments in different directions just to see what could be interesting here. And, all right, another video. So as I said, in the standard scenario, when you control the active player and the rest of the agents are controlled by the built-in AI. And because this AI depends on some hard-coded rules, it may be not necessarily optimal. So for example, here you can see that when we train the agent, when the agent controls only only the active player, in this scenario we are able to get the scoring in 76% of the cases. So this is mostly because the scenario is stochastic. So you may go at the goalkeeper, but it may stop you, etc. Maybe you are too far and the ball will land in a different place. But when we change the assumption, so when we allow the agent to control all the players, it's actually able to figure out a better strategy that scores not in 76, but in, I think, around 97% of the cases. So you can see, okay, the first passes here, say we pass here and score. So let's do this switch again. Okay, so I think this is very interesting because if we train a multi-agent, really with self-trained, all of that things, here we could be maybe able to observe agent learning some very non-intuitive strategies for football. So we all assume that the setup for football should be 1-4-4-3 or something like this. But maybe actually the good setup is 1-10 or 1-5-5. I mean, who knows what the AI would be able to figure out when it has the full control of everything. And there's also room here for other very interesting projects that we already discussed with Henrik a bit, and Piotr, can we train players that are able to easily adapt to other teams? So yeah, I think there's really lots of cool topics here that if you are interested in the environment, would be very interesting from the research perspective. I also wanted to mention briefly, so this is before the premiere, so it's not yet pushed to GitHub, but very, very soon we'll have external game server. And the idea here is that you can train your agent locally, and there is some league that we are running. You can connect. So actually, the only change you need to make is to change football environment to remote football environment, and then you can challenge either Google bots, or you can challenge basically other researchers. And so this should work more or less out of the box. And then, who knows? Maybe we'll organize a competition or something. All right. So if that sounds interesting, how you could get started? So as I mentioned, the whole code is open source. So if you go to here to GitHub, you can figure out all the instructions to run it. We try to make it as lightweight as possible, without many dependencies. So basically, I think this shouldn't take more than 5 minutes based on my test, but obviously my test was biased a bit because I knew it. And what you have to do to run it, as I mentioned, it's already follows the standard OpenAI interface. So you can just create the environment and then call the standard step interface. And that's it. And you can decide if you want to play against it, or you want agent play against agent, or maybe you and agent playing against other agents. So actually this interface is very flexible in terms of controllers. And we also provide some of the pre-trained model on our GitHub, and soon we should provide more of those models as well. All right. And I just wanted to briefly mention that if this kind of projects sound cool, we also do a research internships at Google. If you'd be interested, the application just opened 2 days ago, so you can go to the link and apply. So if you're interested in any of those, feel free to shoot me an email. Here's again the link. I think we have still plenty of time. This is good because I have some bonus. Okay. So this is a paper that was sent to iClear last week. So we have this system, this Google Research Football, and now the question is how you train it, especially how you train it on cloud, because maybe you don't have access to the Google internal cloud, or or maybe you would like to run some kind of actors that are actually not really well supported on board. So a team of researchers from Google Brain created the SIT algorithm, which is very, I would say, extremely scalable type of learning agents with central inference. So based on our internal test, it really scales easily to millions of training steps per second. And it supports environments like a Google Research Football or DeepMind Lab or Atari out of the box. And I think it's already open source, and it should be extremely easy to run on cloud. So this is actually, I'm not aware of other distributed RL system that would be easily integrated. There's Impala v1, that's open source. But other systems, I think, either are internal to DeepMind or Google or Facebook, or they are not really easy to run on those clouds like Google Cloud or Amazon. And so if I had to tell one thing about this, it's if you're familiar with Impala, right? So in Impala, the setup was as follows. So we had some kind of actor that was running the environment, and here, what was happening, at the beginning of every episode, the actor is getting the new policy, and then it's executing this policy, it's creating a trajectory. Now this trajectory is sent to the learner. Okay, and then based on that, the learner does the update of parameters. The difference in SIT, which is also internally called Impala v2, the difference is that we put more work on the learner. So basically, everything is centralized. The only thing that that actor does is sending the observations to the learner, and it's asking it for which action it should execute, right? So here it's running the model, it's getting like multiple observations from multiple actors, it's running on like, I don't know, TPU pod, for example. It gets like everything and just sends the action. So as you can see already, there is like a less of a network overload because we don't have to send the full model. So imagine you have like a very, very large model, let's say with, I don't know, billion of parameters. In the old Impala, you would have to send this huge model to every actor at the beginning of every trajectory. Here, the model lives like fully in the learner. So you can easily scale to really large models, and it's also much cheaper.
So here, how do you deal with delays so that in Impala you have some corrections to accommodate for the fact that there is some shit in distribution between like learner and actor. So is it CP here?
So this is actually the next slide. So actually the seat is much more, in a sense, it's much more on policy, right? Because here, like in the actor, you may get some of the policy, then you're executing your trajectory, and the learner policy changes in the meantime, right? While in seat, what's happening is like, you're just asking the learner for your next action. So in a sense, you are always using the current learner.
Yeah, but it may change in one episode the policy.
Yes. Yeah, it may be that, yes. So it may be that, like you see here in this one trajectory, you actually used 3 slightly different policies.
Is it a problem or it's...
No, it's actually advantage. So...
It's a feature.
Like if I had to sum up, it's like it works at least as good as Impala V1, but it's much faster and much cheaper. So I think it can be seen here. So here is the so if we restrict to so here is the wall time. So here you have time in hours versus the score. So you can see that the blue one is the old Impala. So Impala is much slower actually to get the same results. But in terms, if we just look at the sample complexity, Impala is comparable to the seed that's running on, like, let's say, reasonable number of CPU cores. I mean, obviously, if you go to 12,000 cores, it maybe stops scaling that well, but still it scales much better than Impala. And so here are some of the numbers that I got from because I'm not actually working on this algorithm, I'm just selling it here. That's more seriously. So here you can see that for some kind of environments like a DeepMind lab, actually, like previously with Impala, they were able to run it like maximum with 30K frames per second, because the thing stopped scaling, like the network. So, sorry, question?
Is it important that is it relevant that there is on Impala you try to do it on NVIDIA and in C you try TPU? I think it might be some.
Yeah, but I think the bigger bottleneck here were actually networking and some kind of factors, at least what they told me, because they really try to make the Impala match C. So yeah, I mean, obviously it's not really comparable. Okay, if you take this many environments, but simply you wouldn't be able to take this many environments with the original Impala. Right, and yeah, so here you can see that, like, yeah, in terms of frames, actually the seed is able to match kind of the state-of-the-art algorithms. But like if we look at the wall time, like how long you really need to wait to get your results, we are able to get it much faster. And yeah, so here is some kind of cost of running. And I think the conclusion here was that, so basically you can see that once we increase the size of our models, actually the seed gets like even bigger advantage over the original Impala. All right, so I think we are exactly on time.
For them, but I think that we can allow on like 1 or 2 questions, and then we'll move to the club room. So,
Yeah.
Other questions?
I was wondering, what's the relation between the type of reward you're talking about and some. Did you consider some analytics that are used in actual football analytics for assessing how good is the action? There are some concepts like expected goal value or packing, which is defined as how many opponents are left behind the ball with the pass. So that's how you measure how good the pass is, and it's used to actually assess players. Or some other concepts like, for instance, talking about space, like using the Voronoi diagram to assess for the optimal structure. And can you elaborate, how do you think this, your model and the actual football models are related to each other, which can help which and in which way?
So I would say like we looked at it more as like a pure RL problem, in which like in ideal scenario we wouldn't like to do any reward shaping at all. So like in my ideal world, we solve it with only this goal. Like the same way, like when you train a robot, you would like to give it a task to pick up an item, and don't give like additional reward for like moving hand here and then moving it here and then picking up items. So like we really care mostly about this like pure reward of just scoring. And this reward we introduced because we observed that it really helps a lot, and like when people will be experimenting with it, it will be just beneficial to speed up some of the experiments. But ultimately we hope there will be a method that can just deal from they can just deal with this sparse reward. And the thing that you mentioned, like expected goals, I mean, you can compute it for like real players, but yeah, I'm not sure if we should go into things that are like so super specific to football. I mean, the goal are, I think, the progress in our.
When you compare seed to Impala, since you move the model to the central server in seed, you run into latency issues potentially because you need to send the images back and forth. So for a single CPU, are you running multiple environments so that while you're computing something, you're already sending the image back and forth so that you don't waste the time for the...
I don't know how, I don't know the exact technical details, like how they send it, but I agree that if you have to process the images, it may be tricky, but at least even though in the original Impala you also need to send the images, right? So in the original Impala you need to send the parameter model, the parameters of the model. You need to send the observation and the action, right?
Why? But don't you run the environment locally for Impala?
Yeah, but then you need to send the trace to the learner, the whole trace of the.
True, but this is offline, right? When you finish, you can just upload. But
Yes.
All the time you do it, so you need to balance it.
I mean, there might be some latency issue because even because you still need to wait for the response from the learner. But it's a trade-off. In most scenarios that we analyzed, they were actually blocking, so that wasn't an issue. If you had something which is really real time, maybe you would need to put the learner very closely, let's say in the same data center as the actors.
Okay, so I think that we shall move to the club, which is forum rooms in a while, and there will be also some cookies and possibility to ask more questions to Karol. And now let us thank the speaker.